So we were showing you the plots, the simple MATLAB plots that you can obtain to understand what is the insulating mold condition, and which is now you can clearly see is different from the condition where you impose the external temperature. And this is a simple MATLAB program where the solution has been, the analytical solution has been used, but actually you can also like I have also already mentioned in some of my previous lectures, that you can use MATLAB to write or get the solution from first principle, that is using the thermal heat equations. So you can directly use the heat equations, solve those differential equations and get a plot like this by putting initial and boundary conditions. And then we had looked at the insulating mold condition, which was our, and all of these we discussed in unidirectional heat flow condition. So we looked at the insulating mold condition, where we assume that the heat flow is in only one direction, and we assume that metal has much better characteristics over here, and because of which the conductivity of metal is very high and all the temperature thermal drop takes place only in the mold. And assuming this and taking some boundary conditions, we were able to get solution for this using the thermal diffusivity equation. And then we also obtained S as a function of T and S as a TF, which where TF represents the total time for solidification. For that we assumed that the 3-dimensional objects that we are taking into consideration are simple geometries, and based on those assumptions we were able to get TF as a function of V and A is being the metal mold interface area. So we were able to get these equations using the insulating mold condition. And then we also discussed the implication of slope. You remember we always draw the slope with increasing slope if we go from in mold from air mold interface to the mold metal interface, and this is always increasing, while the slope for the solid going from mold metal interface to the solid liquid interface is always decreasing. And we found that what is the reason? The reason being that solid is actually cooling down from Tm, while mold is getting heated up from T0, the room temperature. And if you assume that there is no interface resistance, there is also a relation between the slopes of the mold metal interface on the two sides, the solid and the mold side. And these are some of the implications or some of the important things that we looked at. Then we also looked at another simple case, or where we took some simplification, some assumptions, and that particular case was interface resistance, meaning a temperature drop is completely taking place at the metal mold interface instead of the solid or the mold part. And we also saw how the temperature plot should look like. It actually looks like for all time it will always have the temperature drop only at the metal mold interface, and it is particularly useful when we are looking into applications like permanent mold casting, die casting, powder manufacturing processes. But when we are talking about these kind of processes, we should also talk about the processes that were involved in the previous one, which was simple sand mold casting. And in the another assumption in here was that the mold is assumed to be infinite in extent, that it means that it remains at its original temperature, which is also the semi-infinite condition that we invoked for the previous case. And we were able to get in the previous case we obtained Svorinov's rule, and here we got solidification time S versus time, which was different, where we saw that S is proportional to T. In the previous case we obtained S proportional to root T. And then we looked at some realistic conditions, two of these, when the mold is chilled and another when the mold is not chilled. So when solidifying metal has significant resistance, and when both metal and mold has significant resistance. So in one of them the temperature drop was taking place in solid, and in the other case temperature drop was taking place in mold as well as in solid. These are a little bit, if you remember we said that these are a little bit more complicated condition, because the temperature drop is taking place in solid and the length extent of the solid is actually changing. So the overall temperature profile is changing, not only because of the change of the heat flow, but also because of the length of the solid region. And second condition is much more general, where you have no chilled mold, meaning you are not doing anything extra to keep the mold at particular temperature. And we looked at solution, although we have not derived it, but we looked at the solutions that have been obtained. And then we went on to alloy solidification that we discussed in just the previous lecture. And there are some very interesting, why I am showing this slide is that there are some very interesting websites, for example this website, where educational website, where you can see animations which explain some of the phenomena in a very vivid way. So it may be very helpful to get a visual understanding of this phenomena. We saw that single phase alloy solidification is different, and it is different because there is a range of temperature for solidification. And we obtained, we did not obtain solution, but we looked at the S versus T plot and looked at the different conditions. For example, when there is no interface resistance, when there is interface resistance, and when there is an insulating mold. So for some of these conditions, we looked at how the S versus T plot should look like and what are their implications. Now that we have gone through all this, it is time for us to look at some example problem that will help you understand exactly what we have been discussing in last few lectures. So to begin with, let's look at this example problem. Aluminum is splat cooled. Remember splat cooling that we discussed about, and we are talking about aluminum. It is splat cooled to room temperature on a copper substrate. So if it is splat cooled, meaning it is started from melting point, and if we have not, its temperature is not given, so you can assume that it started with its melting point which is 660 degrees Celsius, and then it cooled down to a room temperature on a copper substrate. So it hit a copper substrate with a mold metal interface heat transfer coefficient. So it is also given to you that what is the phenomena that is taking place. It is mold metal interface controlled heat transfer. Assuming heat transfer is interface controlled, how thin must the sample be to achieve a cooling rate of 10 to the power 6 Celsius per second. So you are given that it is interface controlled, but now you have to find out what should be the thickness of this of the droplet that has formed a thin layer, how thin this layer should be so that you can get a cooling rate of 10 to the power 6 Celsius per second. Now that looks a little bit interesting problem, because we have never talked about cooling rate so far. So let's look at what do we know and try to solve this problem. We know for interface resistance S is equal to H Tm minus T naught rho S H into Tf. Now if you look at over there, H is given, rho S is given, heat of fusion is given, Tm is given, T naught is given, Tf is something that we don't know, and this will give us the total length which has solidified. So we don't know this, we don't know this, and what we are given or what we have been asked to relate it is with cooling rate. Cooling rate is given as 10 to the power 6 Celsius per second. So now you know what are the data that has been provided to you. You know that cooling rate is given, although we have never talked in terms of cooling rate. But then what is cooling rate? It is only that, in the simplest form, it is the total temperature change taking place in the time. And what is this time? This is the time for solidification. So now we know the delta T, we know cooling rate, which is this, and from here we are in a position to get Tf. And if you put this equation over here, delta T is equal to Tm minus T naught, because we are cooling it all the way to the room temperature. So if you put this over here, you will get Tf equal to So it is the total time for solidification, as you would expect in splat cooling, is coming to 0.64 into 10 to the power minus 3 second, 0.64 milliseconds. So it's a very small time. That will also give you an idea what is the time frame that we are looking at when we are talking about splat cooling kind of phenomena. So this is the total time for solidification. Now the question is, can we put this directly in over here to get S? This S will be the thickness that has solidified in that range, and if that is the thickness of the material, then it would mean that it is indeed this is the time it takes for cooling, and therefore it gets or it achieves this kind of cooling rate, which is 10 to the power 6 Celsius per second. But remember, when we were talking about the total solidification over here, we were saying that H over there that we were taking, it was only equal to heat of fusion. But over here we have some additional amount of heat that is taking place, and that is when we are cooling all the liquid all the way from Tm to T naught, and therefore some additional amount of not the liquid, sorry, the solid is being cooled from Tm to T naught. Additional amount of heat has to be absorbed, because you remember how was the plot over there, interface resistance, this is the mold, this is the solid, this is liquid. So we were only concerned with solid becoming liquid, but we were never concerned with decreasing the temperature of the solid to the room temperature. So there is some additional amount of heat that has to be absorbed to bring the whole solidified splat to room temperature. So that amount of heat has not been taken into account in this original equation, and that is something we need to take into account. Therefore, what we will do, or how do we take into account that additional amount of heat? There is no in the original equation there was no way where we could have included, but since we are taking some approximations, we can say this H can be replaced by this H plus delta heat. And what is that delta heat? C metal into delta T. So the specific heat of metal solid part, the specific heat of the solid times the temperature. So this will become the total amount of heat that is needs to be emitted by the solid, and that needs to be absorbed by the copper to achieve this kind of cooling rate that we have talked about, that 10 to the 6 Celsius per second. So the major difference that we are doing here is we are changing H to a new quantity H plus delta heat, which is H plus Cs delta T. Therefore, your equation becomes so this is a simple simplification that we do, or a simple assumption we do to get to the solution of this problem. And when you put it over here, all the values, you would see that that S comes out to or equal to 6.8 micrometer. So we are talking about a very thin layer, and that is only when you can get a cooling rate of this order, 10 to the power 6 Celsius per second. So we need the droplets must be small enough so that once it splashes onto the substrate, it becomes as thin as 6.8 micrometer, and then you will be able to get cooling rate like this, 10 to the power 6 Celsius per second. So that is the solution for this problem. Now let's solve another simple problem quickly, and this problem is about a large slab of aluminum 25 centimeter thick. It is, when I say large slab, meaning and it is poured, I mean that it is in liquid state. So it has to be made into a slab this much thickness, but to begin with it is in liquid state, is poured in a sand mold with no superheat. How long will it take for the slab to solidify? So we are given that it is a sand mold condition, so you can understand what particular model you need to use. The model that we need to use is the insulating mold condition. It is given that there is no superheat, and from there we have to find how long will it take for the slab to solidify. So let us try to solve this problem. Again, it is this one is not, does not involve much trick over here. This should be straightforward. So we have a aluminum slab, meaning at to begin with it is in the liquid state, and since it is a insulating mold condition, so let us first write down the equation we have. So what you need to find according to the question is how long will it take, and this is the equation where we have S related to T. We need to find T in terms of S. So it is not very difficult, we just write it like this: T is equal to so S is a function of root T. If you want to take find out T, you have to square everything, and then you are able to get T in terms of S. Now here you know all the parameters, you know S, you know rho S, you know H, Tm, T naught, all the parameters are given, and therefore you can just simply plug in the values and you would see that the time comes out to, you have to be careful in about one thing. When you are plugging in the values, make sure that the dimensions remain same. For example, you cannot put a unit per minute somewhere over here and then expect to calculate in seconds. So you have to be careful in selecting the units properly. If you will have to convert it to the right unit so that the dimensions match properly or the units match properly. So this was a simple problem. We had no manipulation to be done over here. We just had to use we have to realize that it is a insulating mold condition. So from the insulating mold condition, we take the S versus T equation and then write T in terms of S, plug in the values, and you get the total time for solidification. So these are the two simple problems that we have looked at, and with that we have come to end for this module, which is the heat flow. Next we will look at the compositional variation. So now we are, so far we have looked at three important aspects of solidification. First was thermodynamics, then kinetics, then heat flow, and now we come to composition variation. And when I say composition variation, you can understand that we are talking only about multi-component systems. A single component system cannot have variation in composition. Now in multi-component system also, let us draw a simple, the simplest multi-component would be two component system. So let me draw one of the simple diagrams for multi-component. Now over here, even in a multi-component, you can get single phase. For example, if we call it alpha, this is a single phase, this is a single phase. There here you have two phases, alpha plus beta. Over here also you have two phases, alpha plus liquid. This is all liquid, this is beta plus liquid. So now we will divide our problem into two parts. One where we get single phase, another where we get double phase. So we will talk about a double phase near the eutectic, that will be the simpler problem to deal with, and single phase region where we are getting only one phase, although the components are two, A and B, but we are getting only one phase. Now even for this single phase that we get, there can be some complications, or let us not say complications, but there can be variations. One would be where you have plane front solidification. So let me define the overall broad class of composition variation that we will be discussing. So plane front solidification of single phase. This is one. Second is, instead of plane front, you may get cellular solidification, or where you are not getting plane front of solidification. So we will have cellular So this is, these two are related with this single phase. Another broad class would be the multi-phase or polyphase. So here we will look at plane front we will not get into, even in the plane front, you will see that you will have more than one phases getting formed, but we will not get into the cellular solidification of polyphase alloys as of now. We will keep it simple and we will discuss only these three. So these are the three broad classes, and even amongst these you would see there are several some subclasses you can see, and we will touch upon them as and when we get to them. So first we will start with the plane front solidification of single phase alloys. Now whenever we are trying to consider solidification of such kind of alloys, then it is appropriate to make some assumptions. Otherwise, if we do not take any assumption, then it will be very difficult to formulate any kind of understanding. So some of the assumptions that we inherently take when we are talking about these, one of them is equilibrium at interface. What do we mean by equilibrium at interface? So in the interface is, here is the solid and the liquid interface. So when we are doing the solidification at the just at the interface, we always assume in these cases that there is equilibrium, meaning the solid and the liquid atoms can easily join or detach, basically based on what is decided by the phase diagram. So if we have taken a composition like this, and we are at a temperature like this T, then this is the composition of the solid part CS, this is the composition of the liquid part which is Cl. So when we say equilibrium, what we are saying is that the solid is at a composition Cs and liquid will always be at the composition Cl. So for a given temperature Cs and Cl will get fixed, or the three combinations will be always the three will always have fixed relation with each other. If you fix T, you would know Cs and Cl. If you fix Cs and Cl, you can say what is the temperature. So the in effect equilibrium at interface is saying that at a particular temperature Cs and Cl are given by phase diagram. So this is an assumption that we make when we are talking about plane front solidification. Another assumption that we take is regarding the partition ratio. What is partition ratio? The term Cs by Cl. So you see we have drawn Cs, or for this particular temperature you have a Cs value and a Cl value. Then for the ratio of this Cs by Cl is called, or given a term K, which is the partition ratio, and it has an important role to play. It determines that for a particular temperature what will be the solute concentration in the solid part and the liquid part. So that is why it is called partition. What fraction of solute is in the solid and what fraction of solute is in the liquid, that is determined by K. But as you can see, if you go from one temperature to another, this is Cs by Cl, over here it will be different, here it will be different, the Cs by Cl ratio would be very, very different, and therefore this is not easy to again mathematically understand, or mathematically you can say formulate, and therefore another assumption is taken is that of straight line liquidus solidus. Now this is a very, very interesting assumption, as you will see. Instead of taking these as curved as they actually appear in the phase diagram, for the purpose of understanding, we take these as straight lines like these. Can you think of a reason why we take it as a straight line? We'll think about it until the next class, and we'll come back at this point in the next lecture. Thanks.